We now discuss the solution of a problem from the section Real Analysis, and the problem is on continuous functions. This question appeared in CSIR NET National Eligibility Test held on 26th November 2020, and it is from the section B and it carries 3 marks. The problem is given f and g are continuous functions defined on the closed and bounded interval 0, 1 such that f of 0 is equal to f of 1 is equal to 0, g of 0 is equal to g of 1 is equal to 1, and f of 1 by 2 greater than g of 1 by 2. Which of the following statements are true? Option 1. There is no t belongs to the closed interval 0, 1 such that f of t is equal to g of t. Option 2. There is exactly one t belongs to the closed interval 0, 1 such that f of t is equal to g of t. Option 3. There are at least 2t belongs to the closed interval 0, 1 such that f of t is equal to g of t. Option 4. There are always infinitely many t belongs to 0, 1 the closed interval such that f of t is equal to g of t. Let's now discuss the solution of the problem. We are given two continuous functions f and g defined on the closed and bounded interval 0 to 1 such that f of 0 is equal to f of 1 is equal to 0, g of 0 is equal to g of 1 is equal to 1, and the f of 1 by 2 greater than g of 1 by 2. Let's now define a new function h of t is equal to f of t minus g of t for all t belongs to the closed interval 0, 1. Now, h is a continuous function because f of t and g of t are both continuous functions defined on the closed and bounded interval 0 to 1. So is h is continuous on 0, 1. The value of h at 0 is equal to f of 0 minus g of 0. f of 0 is 0, g of 0 is 1, 0 minus 1, that is negative. h at 1 by 2 is equal to f of 1 by 2 minus g of 1 by 2 is greater than 0 because f of 1 by 2 is greater than g of 1 by 2. It is given. We now recall an intermediate value theorem. This theorem states that if f is a continuous real valued function defined on the closed and bounded interval a, b, and f of a and f of b have opposite signs, that is f of a multiplied by f of b is negative, then there exists at least one point c belongs to the open interval a, b such that f of c is equal to 0. Here h of t is having opposite signs. h of 0 is minus 1, h of 1 by 2 is greater than 0, and they have opposite signs in the interval 0 to 1 by 2. So by intermediate value theorem, there exists at least one point x belongs to the open interval 0, 1 by 2 such that h of x is equal to 0. And now h of 1 by 2 we have already seen it is greater than 0, and h of 1 is equal to f of 1 minus g of 1. f of 1 is 0, g of 1 is 1, 0 minus 1 is minus 1, which is negative. Again, we apply the intermediate value theorem. By intermediate value theorem, there exists at least one point x belongs to the open interval 1 by 2 to 0 such that h of x is equal to 0. So there is at least one point x belongs to the open interval 0 to 1 by 2 such that h of x is equal to 0. There exists at least one point x belongs to the open interval half to 0 such that h of x is equal to 0. We continue in the next slide. This is what we have from the previous slide. Thus, there exists at least 2 points t belongs to the complete interval 0 to 1 such that h of t is equal to 0. That is, h of t means f of t minus g of t is equal to 0. That is, f of t is equal to g of t. So, there exists at least 2 points t belongs to the closed interval 0, 1 such that f of t is equal to g of t. So, this shows there are at least 2 points t belongs to the closed interval 0 to 1 such that f of t is equal to g of t. Let us look at the options there. The third option is true. And now obviously the first option is not true because there is no t such that f of t is equal to g of t. And the option 2, there is exactly one t belongs to 0 to 1 such that f of t is equal to g of t is also not true. So, the options 1 and 2 are not true. We are left with the fourth option. There are always infinitely many t belongs to 0 to 1 such that f of t is equal to g of t. So, we will discuss about the option 4 in the next slide. Option 4 is here and we will see the validity of this statement. And we will show that this is not the case, that this is not true. So, for that we consider a counter example. Let f of t is equal to capital A t square plus capital B t plus capital C and g of t is equal to a t square plus b t plus c in small letters. And clearly, because they are polynomials, they are continuous functions on the closed and bounded interval 0 to 1. And f of 0 is equal to 0. The conditions we will lay down. What are the conditions? F of 0 is equal to 0. That will give you c is equal to 0. F of 1 is also equal to 0. F of 1 is 0 means a plus b plus c is 0, a plus b is 0, b is equal to minus a. Then f of t will be a t square minus a t into t minus 1. Now, g of 0 is equal to 1, g of 0 is equal to 1. So, 0 plus c, that is equal to 1, c is equal to 1. G of 1 is also 1, that is a plus b plus c, that is c is 1 is equal to 1, 1 cancels, a plus b is equal to 0, that implies b is equal to minus a. Therefore, g of t is equal to a t square minus a t plus 1, that is a into t times t minus 1 plus 1. Now, f of 1 by 2 greater than g of 1 by 2. So, that will give you and t is equal to 1 by 2 value, you put a into 1 by 2 into t minus 1 by 2, 1 by 2 minus 1, that is minus 1 by 2, minus 1 by 2 plus 1 by 2 minus 1 by 4 minus a by 4, which is greater than here similarly minus small a by 4 plus 1. And cancel the minus sign throughout and multiply by 4, we get the inequalities get reversed. Capital A is less than a minus 4. To be specific, let us take the value small a is equal to 1 and thereby capital A is to be chosen and we have chosen as minus 4. Small a is 1 means 1 minus 4, that is minus 3, and capital A is to be chosen less than minus 3 and we have chosen capital A is equal to minus 4. Therefore, f of t is equal to minus 4 times t into t minus 1 plus g of t is equal to t times t minus 1 plus 1. These are the two continuous functions defined on the closed and bounded interval 0 to 1 with the given properties. Now, f of t is equal to g of t will imply minus 4t into t minus 1 is equal to t into t minus 1 plus 1. And that is this one. And this will give rise to the polynomial phi of 5t square minus 5t plus 1 is equal to 0. This being a quadratic in t, we solve it and we find the solutions as t is equal to 5 plus or minus root 5 by 10, which belongs to the closed and bounded interval 0 to 1. So thus, this example shows f of t is equal to g of t at 2 points t belongs to 0 to 1. We do not have infinitely many t belongs to 0 to 1 such that f of t is equal to g of t in this example. So therefore, there are always infinitely many t belongs to 0 to 1 such that f of t is equal to g of t is not true. Thus, the option 4 is not true. So, on the whole, the final answer is option 3 is true, option 1, 2 and 4 are not true. This is the discussion of the solution of the problem from the section real analysis, and the question is on continuous functions. I hope that you have understood the solution of it, and I wish you all the best. Thank you.